Hello, welcome to another lecture in this course on 3G, 4G wireless communication systems. In the last lecture, we had talked about MIMO OFDM, that is what is the use of OFDM technology in MIMO wireless communications. We said that MIMO OFDM converts a MIMO frequency selective channel into a set of parallel MIMO flat fading channels such that across each subcarrier the net wireless communication system looks like a MIMO flat fading system, that is vector y0 is now h0 times x0, where x0 is the transmit vector across the 0th subcarrier, h0 is the channel matrix and y0 is the receive vector across the 0th subcarrier. Similarly, the first subcarrier so on till the n minus 1th subcarrier, where y n minus 1 is the r dimensional receive vector, which is equal to h, the matrix h n minus 1 across the n minus 1th subcarrier, and x bar n minus 1, where x bar n minus 1 is the transmit vector across the n minus 1th subcarrier. All right. And we had also seen that for the purposes of receiving across each subcarrier, now similar to MIMO, we can either use the MIMO 0 forcing or the MIMO MMSE equalizer, that is we can use similarly to what we had seen in the case of MIMO systems, we can use both 0 forcing and MMSE equalizers. And with that, we had also said that these channel matrices, now how do you obtain the channel matrix across each subcarrier? We said that if you consider the uvth element of all these channel matrices across each subcarrier, that is there are n such elements from 0 to n minus 1, they are nothing but the n point FFT of, if you take all the channel taps matrices, that is H0, H1, HL minus 1, take their uvth element, they are L such elements, and then you 0 pad them and take the n point FFT of these elements, then you will get the uvth element of the channel matrices across the subcarriers. You can similarly do that for all the elements and thus construct essentially the channel matrices for the subcarriers. All right. So, that is how you construct these channel matrices in this MIMO OFDM system. It is fairly straightforward and an extension of the case for the single input single output OFDM system, but it is much more helpful in MIMO system because MIMO equalization, that is MIMO frequency selective channels, pose a much more bigger challenge for communication compared to single input single output frequency selective systems. All right. So, that is the basic idea behind MIMO OFDM, and then with that we had moved on to the effect of frequency offset. What is the distorting effect of frequency offset in OFDM system? We said OFDM divides the frequency band into a set of orthogonal overlapping yet orthogonal frequency carriers. The orthogonality is a very critical aspect actually of any OFDM system, which means once you have an OFDM system, as we had depicted through this figure last time, the orthogonality is lost, which means now there will be ICI or inter-carrier interference. The carriers will start interfering with each other, and the larger the frequency offset, the greater is this inter-carrier interference. Hence, this is a very, how you deal with frequency offset is in fact a very important aspect of any OFDM system. And we had also started seeing how to model the effect of this intercarrier interference as well as this frequency offset. We had said for a frequency offset of epsilon normalized with respect to the subcarrier bandwidth, the received signal, the received sample yn is given as summation xk hk e power j 2 pi n k plus epsilon over capital N number of subcarriers plus noise. That we said is the system model for this. And then we had started looking at what is the effect when you take the FFT of this received samples. Now, with the presence of carrier frequency offset, what is the effect of this on the FFT? That is what we started looking at that. So, with that, let us go on to today's lecture. So, we said that YL, that is what we said is, we said YL is nothing but, you consider, that is the received symbol across the Lth subcarrier is nothing but consider the FFT of the received samples as in this fashion, that is summation received samples yn e power minus j 2 pi nl over n. Let me remind you, this is the Lth FFT point, which is the Lth received symbol across the Lth subcarrier. This is the received symbol across lth subcarrier. This, using the expression that we had earlier, this can be simplified as follows. This is nothing but 1 over n summation k equals minus n over 2 to n over 2 x k h k e power j 2 pi k minus L plus epsilon over n. That is, I am doing nothing but I am simply substituting the earlier expression that we had for the nth sample y n in this expression, that is x k h k e power j 2 pi, the expression that we had earlier. I am simply substituting it over here, plus the noise part, which is plus summation over n w n e power minus j 2 pi n l over n. So, I have the expression for y n, that is the nth received sample. I am simply substituting that expression in this, that yields me this. Now, what I am going to do is, from this term over here, from this first term over here, I am going to isolate the term corresponding to k equals to L. This is similar to what we had done earlier, because I want to look at this as two terms. One is the desired part, which is what I am supposed to receive on the Lth subcarrier, that corresponds to k equal to L, and then the interference part, that corresponds to all k not equals to L. So, I am simply going to write this as a summation of two terms. Now, when k equals L, this goes to 0, so this simply reduces to x L h L e power j 2 pi epsilon over 2 pi epsilon n. There should be an n here, there is an n missing, 2 pi epsilon n over n. So, I am going to write this as summation 1 over n n x L h L e power j 2 pi n epsilon over n. Now, remember, if there was no carrier frequency offset, then this epsilon would have been 0, this would have been 1, this would have been summation 1, which would have been n over n, this is 1. So, this would have yielded our x L h L, similar to what we had earlier. Now, because of this carrier frequency offset, this is not exactly 1, all right, that is the problem here, plus summation 1 over n. Now, k equals minus n over 2 to n over 2, however, k not equals L, because we have isolated the term k equals L, summation over n, this is x k h k e power j 2 pi n over n into k minus L plus epsilon, okay, plus some noise, which is w tilde of L, plus some noise. So, what we are doing is, I am taking the expression for the received nth sample, I am substituting it in the FFT expression, FFT at the FFT expression, that is the Lth FFT point, and thus I receive, I am formulating the expression, or I am deriving the expression for y L, which is nothing but the expression for the received subcarrier, received symbol across the Lth subcarrier, and that is given by this expression. Okay. And that can be further simplified. Before I simplify that further, I want to illustrate a result. The result I want to write here is the result that I will use in simplification, that is as follows: summation n equals 0 to n minus 1 e power j theta n equals, you can verify this and it is a simple problem of a geometric progression. This is sin n theta over 2 divided by sin theta over 2 into e power j phi tilde, where this phi tilde e power j phi tilde is some phase. So, this is essentially some phase factor. We do not care about this phase factor because it does not affect the power. What I want to illustrate is what is the impact on the signal to noise power ratio. So, magnitude e power j phi is 1. So, this does not affect the phase, however, this does not affect the power. However, this is the sin n theta by 2 by sin theta by 2, this is the critical factor for us, all right. So, this for us, this is a do not care as it does not affect power. That is why I am not particular about this. This is do not care as it does not affect, and it does not affect the net received signal power. Okay. So, this now can be written as YL, this can be written as YL equals HL XL sin pi epsilon divided by sin pi epsilon divided by n into 1 over n into e power j some phi L tilde. Okay. All right. Now, again you can verify that if epsilon equal to 0, limit epsilon tending to 0, this tends to n, n into 1 by n, this tends to 1, this is HL XL, this is the same thing as we had before, plus what we have here is summation k equals minus n by 2 to n by 2, k naught equals L HK XK sin pi epsilon divided by n sin pi L minus k plus epsilon divided by n into e power j phi k L tilde. This is the interference term I L, this is the interference term, this is the net interference now, which is not equal to 0 because of loss of orthogonality, because of the presence of this frequency offset sign, because you can see if this epsilon is 0, this whole interference, this goes to 0. Now, because of the presence of a carrier frequency offset, you end up having this intercarrier interference, and this is nothing but the interference from all the other subcarriers other than the Lth subcarrier plus W tilde L. All right, this is the expression that we have. So, this I would like to say. So, this is the signal part for this here, this is the signal part, that is the desired signal part. This part here, this is the intercarrier interference part. And this, of course, this is our Gaussian noise, this is our thermal noise or Gaussian noise. All right. So, let me just call it this as Gaussian noise. Okay. So, this has three parts, one is the desired signal, the other is the intercarrier interference, and then again you have the Gaussian noise part. alright. So, now similar to CDMA, we said now we don't not only have signal and noise, but we also have signal, interference and noise. Hence, in such scenarios we use the signal, not signal to noise ratio, but signal to interference plus noise power ratio. So, now we want to characterize the SINR as SINR equals signal power divided by interference plus noise power equals signal power divided by expected interference power plus the noise power. So, this is signal power divided by interference power is nothing but expected IL square plus sigma n squared, which is the noise power. Okay. So, now let us start characterizing each term, that is, first I want to characterize the signal power, then the interference power, then the noise power. So, let us start with the signal power aspect of this. So, there are three aspects. So, first is, so as we saw, there are three aspects: the signal power, interference power and the noise power. I am starting by characterizing the signal power. The signal power is nothing but, we can see this is expected magnitude HL square into expected magnitude XL square into sin pi epsilon divided by n sin pi epsilon divided by n whole square. Alright. So, this is the signal part, that is expected magnitude HL square, that is the gain of the channel across the L subcarrier, expected XL square, which is nothing but PL, which is the power transmitted across the L subcarrier, or if we are using uniform power, then this is simply P times sin pi epsilon divided by n sin pi epsilon by n whole square. Alright. Now, we are going to assume the limit in which there are a large number of subcarriers, that is, I am going to simplify these expressions further to get an idea of how these expressions look like when the number of subcarriers is large, and typically the number of subcarriers is very large, it is of the order of n equals 512 or n equals 1024. So, how does this expression look when n tends to infinity? So, for large n, that is number of subcarriers, we have limit n tending to infinity sin pi epsilon over n as n tends to infinity, pi epsilon over n approximately tends to 0, that is limit sin theta becomes very small. In the limit theta becoming very small, sin theta approximately tends to theta, hence this is approximately pi epsilon over n for very large n, implies n sin pi epsilon over n tends to n into pi epsilon over n equals pi epsilon. Hence, for a large number of subcarriers n, n sin pi epsilon over n approximately looks like pi epsilon. Hence, this expression for signal power can be simplified as follows. Hence, the signal power for a large number of subcarriers, for n is given as expected mod h square power sin pi epsilon divided by pi epsilon square, where p, remember this p is the power in the signal, this is p is nothing but expected XL square, which is the power in the symbols transmitted across the nth subcarrier. This is power, this is nothing but the power, the signal power or the symbol power. Hence, this is nothing but, and I am going to assume that expected HL square is the same across all subcarriers, since this is P magnitude H square, where magnitude H square is nothing but expected magnitude HL square, that is the average gain across the subcarrier, times sin pi epsilon divided by pi epsilon whole square. So, this is nothing but the signal power. So, we have simplified the expression for the signal power in the presence of a large number of subcarriers, and the signal power in the presence of a carrier frequency offset of epsilon approximately looks as P, where P is the transmitted power, magnitude H square which is the average gain across the subcarrier, times sin pi epsilon divided by pi epsilon whole square. This is the key factor. Okay. Now, let us characterize the slightly difficult part, which is the interference power, the more elaborate part, which is the interference power. So, how does the interference power look like? How does the interference power look like? If we look at the interference power, we said interference power is nothing but expected magnitude I L square, that is equal to expected magnitude x square, expected magnitude HL square into summation k equals minus n by 2 k naught equals n, k equals n by 2 times sin pi epsilon n sin pi L minus k plus epsilon divided by n, this whole square. Remember, where this simplification sin pi epsilon by sin pi L minus k epsilon, this is arriving from this property that we looked at here. All right. Remember, we introduced a special property over here, and this simplification is simply arising from this property. Now, I will have to do, now I will do a series of manipulations which are slightly cumbersome, but I ask you to, but fairly simple also. So, I ask you to just pay attention, because there are more mathematical manipulations rather than anything else, but the idea is essentially to simplify this expression. So, what I am going to do here as a first step to simplify this, I am going to set k minus L equals u, just do a simple substitution, k minus L equals to u, and also assume n tends to infinity, that is the number of subcarriers n is very large, and hence this expression can be simplified as follows: expected magnitude IL square equals P magnitude H square, okay, summation u equals minus infinity. Remember, I have now substituted k minus L equals u, and at the same time k naught equals L, which means u naught equals 0, sin pi epsilon whole square divided by n sin pi u divided by n whole square, where in the denominator I have used the approximation u plus epsilon approximately equal to u, because remember epsilon is a very small quantity and u is varying from minus infinity to infinity. So, for large u plus epsilon is approximately the same as u is in epsilon, in fact a small fraction. Okay. So, this is the net expression that we get, and hence this can be further simplified as follows, that is the interference power, which is P times magnitude H square, also sin pi epsilon square, this comes out of the summation what do we have here, u equals minus infinity to infinity, u naught equals 0, 1 over sin pi u divided by n whole square. Now, sin theta, now I want to use some approximation here. The first approximation I am going to use is that sin theta is greater than or equal to 2 theta over pi. So, sin theta is greater than or equal to 2 theta over pi. I want to use this for this term sin pi u by n, which means I can write this as sin pi u divided by n is greater than or equal to 2 pi, that is 2 theta, where theta is pi u divided by n, 2 pi u divided by 2 theta divided by pi equals 2 u divided by n, implies n sin pi u divided by n greater than or equal to 2 u, and hence now I can simplify this expression here by simply approximating bounding this expression as follows. I can bound this expression as expected IL square is, since n sin pi u by n greater than or equal to 2 u, expected IL square is in fact less than or equal to, because this term is in the denominator, this is P magnitude H square sin pi epsilon square summation u equals minus infinity to infinity, u naught equals 0, 1 over 2 u whole square. All right. So, that is the net approximation that we have over here, and this can be further simplified as follows. This is equal to, I will do a series of manipulations, P magnitude H square sin pi epsilon square times 2. I will write the integral from u equals minus infinity to infinity as 2 times the integral u equals 1 to infinity 1 over 2 u square. This is nothing but half p magnitude h square sin pi epsilon square summation u equals 1 to infinity 1 over u square, all right, and this is simply the sum 1 over u square, where u is the set of all positive integers, and this has a standard this we know the result of this summation, this is simply pi square over 6. Hence, this is nothing but pi square over 12 into p into magnitude h square sin square pi e, which is essentially nothing but 0.822 times p magnitude h square sin square pi into epsilon, all right. So, this is the net expression for the interference power. Hence, now I can write the SINR. Hence, what we have done is we have again derived the power for the expression for the interference power, which is 0.822 times p times norm h square sin square pi epsilon, and also you can observe as a sanity check, if epsilon equal to 0, this is 0, that is there is no intercarrier interference, and hence interference power is 0, which is what we expect. Hence, this is nothing but the SINR. Hence, the net SINR, hence SINR in the presence of carrier frequency offset of epsilon is given as SINR equals p magnitude h square sin pi epsilon divided by pi epsilon whole square divided by 0.822 p magnitude h square sin pi epsilon whole square plus sigma n square, where sigma n squared is a noise power, and this is the expression for the SINR in the presence of carrier frequency offset. Let me remind you again, this is the signal power, this is the interference power from intercarrier interference, this is the noise power. Okay. This is the noise power. So, now we have derived the signal to interference noise ratio in the presence of carrier frequency offset of epsilon, all right, which is p magnitude h square, where magnitude h square, remember, is the average gain across each subcarrier, that is expected HL square sin pi epsilon by pi epsilon whole square divided by 0.822 p magnitude h square plus sin pi epsilon square plus sigma n square, which is the thermal noise. Okay. So, this is the net expression, and you should verify that in the absence of carrier frequency offset, that is the epsilon equals 0, this reduces to simply p magnitude h square divided by sigma n square, which is essentially the expression for the original OFDM signal to noise power ratio without any intercarrier interference, all right. So, you should verify that. In fact, it is straightforward. If you look at this, it's directly visible. If you look at this expression, this tends to 1, the numerator sin pi epsilon by pi epsilon tends to 1 if epsilon is 0, and this denominator, the interference, tends to 0. Hence, this is the expression, all right. And also remember, this expression is an approximation. It is valid under the reasonably good approximation in which the number of subcarriers n is tending to infinity. The approximation, one of the approximations is that is large number of subcarriers. Okay. So, that is what we have here. Now, let us do a small example. So, let us illustrate a small example to illustrate the performance of the SINR under the presence of carrier frequency offset. Consider a system with average subcarrier power gain as unity. That is, consider an OFDM system such that magnitude h square equals unity, that is the average gain of the subcarrier, and we also consider a scenario with signal power or transmitted symbol power P equals 10 dB and sigma n square equals 0 dB, that is the signal to the symbol to noise power ratio P over sigma n square equals 10 dB. Okay. Now, in the absence of a carrier frequency offset, if epsilon equals 0, then we have SNR received is nothing but SNR at receiver equals P magnitude h square divided by sigma n square, which is equal to 10 dB. So, we have a 10 dB SNR in the absence of any carrier frequency offset, that is if the receiver and transmitter are perfectly, that is if the carrier oscillator is perfectly synchronized to the incoming carrier wave, then we have an SNR of 10 dB. There is no intercarrier interference. However, if the carrier frequency offset, consider now a slight distortion, consider a carrier frequency offset epsilon approximately equal to 5%. Consider a carrier frequency offset epsilon equals 5% equals 0.05. Consider a carrier frequency offset epsilon equals 5% equals 0.05. Then we have the SINR equals, remember SINR equals P, that is 10 into magnitude h square into sin pi epsilon divided by pi epsilon whole square, that is sin pi into 0.05 divided by pi into 0.05 whole square divided by 0.822 into P, it is 10 into sin pi epsilon, which is 0.05 sin pi of 0.05 whole square plus sigma n square, which is the noise power, which is 1, and this can be shown to be, you can verify this by computing, this is 8.25. Previously, in the absence of carrier frequency offset, the SINR was 10 dB, which is 10. Now, as the carrier frequency offset has increased to, that is, if we have a carrier frequency offset of 5%, the SINR has dropped to 8.25. Hence, the reduction in SINR equals 10 minus 8.25, which is 1.75, which is essentially 17%, which is equal to a 17%, because out of 10 the decrease is 1.75, which is essentially corresponds to 17.5% reduction in SINR. Okay. So, because of a carrier frequency offset of 5%, epsilon equals 5%, there is a 17.5 reduction in SINR. Let us look at what it means to have a carrier frequency offset of 5%. Now, we said 5% is the net is normalized to the bandwidth of the subcarrier. Let us go back to our Ymax example. Our Ymax, we said that is fixed profile Ymax. It has roughly, it has, let me remind you, it has 256 subcarriers, alright. Each of bandwidth, the subcarrier bandwidth Bs equals subcarrier bandwidth equals 15.625 kilohertz. We said the bandwidth per subcarrier is 15.625 kilohertz. So, 5% of 15.625 kilohertz, that is the frequency offset. So, the frequency offset net absolute terms is equals 5 by 100 into 15.625 kilohertz, that is equal to 0.78125 kilohertz, that is approximately 0.78 kilohertz. Alright, so the net frequency, the absolute frequency offset of 5% in this Ymax system, it means that it is about 0.78 kilohertz, but Ymax we said operates in the 2.4 gigahertz band. So, if you look at this absolute frequency offset as a percentage of the net carrier frequency, so what is the percentage of this frequency offset at 2.4 gigahertz? So, the percentage at 2.4 gigahertz carrier equals 0.78 divided by 0.78 kilohertz divided by 2.4 gigahertz, which is essentially 2.4 into 10 to the power of 9, and if you look at this is approximately, this is equal to essentially 0.78 divided by 2.4 into 10 power 6. So, if you can look, if you look at this, this is an extremely small fraction. If you look at this, this is 0.78 kilohertz and at 2.4 gigahertz, this is roughly the fraction. So, if you look at this, this is an extremely small fraction. In fact, this is approximately equal to 1/3 into 10 power minus 6, that is it is of the order of 10 power minus 6. So, what this means is at the gigahertz frequency, when your carrier at 4G wireless system is at gigahertz, even if you have a carrier frequency offset that is roughly 10 power minus 6 fraction of that carrier frequency, or roughly 10 power minus 4%, that is 0.0001% of that carrier frequency, that can result in a huge SNR, in fact 17.5 or 20% decrease in the SINR at the receiver, right? Which means that carrier synchronization at the receiver in this 4G wireless OFDM system is a very critical aspect, because if the number of subcarriers is of course typically large, that is 256, and as you progress to higher and higher bandwidth, the number of subcarriers is going to increase, that is 256, 512, 1024, which means that your synchronization also has to improve, because even if you have a small carrier frequency offset at the receiver, that means intercarrier interference, which means interference from a large number of subcarriers and a tremendous decrease in the SINR at the receiver. That is what this seems to imply. So, carrier synchronization is a very, very critical aspect of any OFDM system, because if the carriers at the transmitter and the receiver are not synchronized, then we have serious intercarrier interference, which results in a tremendous decrease in the SINR at the receiver. Okay. So, with this we finish the topic of the impact of distorting effects on OFDM, that is the impact of carrier frequency offset. I urge you again to go through this material again to enhance your understanding of the various expressions that we have derived for the impact of the SNR, in fact the signal power, the interference power, and what is the signal to interference noise ratio, and what is and for some reasonable carrier frequency offsets. In fact, we have looked at the example, what is the impact in a practical scenario, what is the impact of having a carrier frequency offset of 5% at the receiver, and so on. All right. And next I want to address one more practical issue, another equally important if not more significant practical issue in an OFDM, which is related to the PAPR, that is peak to average power ratio. So, I want next issue I want to address in this context is the PAPR issue in OFDM. This is the PAPR issue in an OFDM system. What does PAPR stand for? PAPR stands for PAPR equals peak, it requires peak to average PAPR stands for, simply stands for peak to average power ratio, and simply put this is a critical factor in OFDM. This is critical in an OFDM system. What does this PAPR issue mean? For instance, consider a typical non-OFDM transmission system. Let us go back for a moment to understand this. Let us go back to a single carrier system. Consider a non-OFDM or single carrier system. OFDM is a multi-carrier system. So, I am saying just let us go back and consider our single carrier system. For instance, consider a typical BPSK with BPSK modulated symbols. Consider a single carrier system with BPSK modulated systems. We have, let us consider its transmitted symbol sequence of x0, x1, x2. Now, each of these is plus or minus A. Let us say the amplitude level is A, and the information depending on the phase is plus A or minus A, that is for a plus 1 you transmit plus A or minus 1 you transmit minus A. So, we have plus A, let us say the next symbol is minus A, plus A, and so on. Now, if you look at this sequence, what is the power in each symbol? The power in each symbol is each symbol is either plus or minus A. In both cases the power is simply A square, that is expected x square, which is simply A square. So, the power in each symbol is A square, which is also the peak power, because if you look at it, the power in each symbol is the same. So, the peak power is A square as well as the average power is also A square. So, this is also the peak power . How about the average power? Equals expected magnitude x k square. The average power is also A square. Hence, both peak power and average power in this single carrier system are A square, where A is the transmitted amplitude. Hence, both peak and average power equal to A square. Hence, the ratio of peak power to average power equals 1. In practice, it is not exactly 1, it is close to 1 because of pulse shaping and so on in the baseband, but for all practical purposes, I can say the peak to average power in a single carrier system is close to 1, which is essentially you can write this also in dB terms as 0 dB. That is, there is no, so if you look at the mean power level, that is, there is no significant fluctuation of the power over the mean, that is both the mean and the peak power, that is we look at the power instantaneously, that is it is closely tied to the mean, that is there is no significant deviation about that mean. Sometimes you can have a signal which has some mean, but there can be significant positive and negative variations about the mean, so that the net average is the same, but the deviations is higher. What we are saying here is that both the mean is same and the peak is also same, which means the deviations about this mean are also controlled, essentially. That is what this means, that is what this says. Hence, there is no significant deviation from the mean power level. Hence, this ratio close to 1 also means, hence there is no significant deviation from the mean power. Hence, there is no significant deviation from the mean power level. Alright, so we looked at the PAPR, the peak to average power ratio in the traditional conventional single carrier system, and we said that it is close to 1, that is the mean power is A square, the peak power is also A square, hence there is no significant fluctuation of the instantaneous power over the average. So, because of lack of time, we are going to stop here and we will start from this point and continue this discussion in the next lecture, when we look at how does the PAPR look like in an OFDM system. Thank you very much.